Section 1.7 Linear Independence. We're going to start by looking at an example. First, we want to consider the matrix equation AX equals 0, where A is the matrix that we have here, which is a 3 by 3. And so we can see here that as a matrix equation, we have our matrix A multiplied by the vector x and set then equal to the 0 vector. And as a vector equation, we simply have the first column of A multiplied by the first variable x1 in our vector x, and we do that on down the line with x2 and x3. One thing that we know, it has the trivial solution, meaning that our variables are all at least equal to 0 and would make this set true. So we know that for our homogeneous system here, we always have the trivial solution. So then the question remains, is there a non-trivial solution? Before we answer that, we need to introduce some new terminology. In general, if there is a non-trivial solution to the vector equation, given here, where we have x1 times our vector v1 and so on to xp times our vector vp equal to 0, that is, if there exist weights c1 through cp that are not all 0, so that when we multiply those by our vectors v1 through vp and have this linear combination here, then the set of vectors v1 through vp is said to be linearly dependent. So if I have a non-trivial solution to my vector equation, then my vectors are linearly dependent. We also then can say that the vectors are linearly dependent. The set of vectors is linearly dependent and each one is linearly dependent. And this equation is called a linear dependence relation. If the only solution is a trivial solution, then the set of vectors is said to be linearly independent in that case, and our vectors are also linearly independent. So let's look at an example. Here I have three vectors, v1, v2, and v3 in R3 space. They each have 3 entries. And we're going to do two things. First, we want to determine if the set of vectors is linearly independent. So we want to find out if we have only the trivial solution. And then, if possible, we want to find a linear dependence relation among our 3 vectors. And so when we say if possible, that would happen only if we have a non-trivial solution. So let's look at the answer for A. We're going to set up the augmented matrix for our linear system, where we have a matrix and the columns of the matrix are our vectors v1 through v3 multiplied by my vector x and set equal to the 0 vector, and then we want to reduce it. So here's my augmented matrix, and to reduce it I'll multiply here by -3 and add to the second row, and then also multiply by -5 and add to this last row here. And we'll get this matrix here. And we have an additional step here. I want to get a 0 underneath, so I'm going to just multiply by -1 and add. And we get this matrix here. And we see we have a row of all zeros, and so we have no pivot in this third row. So at this point then we can see that x1 and x2 are our basic variables and x3 is free. And since we have a free variable, we know then that a non-trivial solution does exist. And so then we can say that v1, v2, and v3 are linearly dependent. They're not independent, they are dependent. So since they're dependent, we can find a linear dependence relation among our vectors, and so we want to continue on. So I'm going to write the matrix that I stopped with when I had a row of all zeros, and we're going to continue in our row reduction. I'll multiply through by a -1, and we get this matrix, and then I'll multiply by a -2 and add upward, and we get this matrix. And so then we can solve here and see that we end up with x1 equal to -33x3, x2 being equal to 18x3, and then x3 is free. So to find our linear dependence relation, we can choose any non-zero value for x3. So let's say that x3 is 1. And when we do that, then we'll get that x1 is equal to -33 and x2 is equal to 18. So we have our vector equation where we replace our x1 x2 and x3 with the solutions that we just found. Or we could write it using just our vector notation. So I'd have -33 times v1 plus 18 times v2 plus 1 times v3 equals the 0 vector. So this is just one possible linear dependence relation. Had we chosen a different value for x3, we would have gotten another relation. So a linear dependence relation such as the one that we just found could also be written as the matrix equation, where we are taking our variables that we found for x1, x2, and x3, and we're replacing those in our vector x here. So then this is the non-trivial solution x to our homogeneous equation ax equals 0. Each linear dependence relation among the columns of A corresponds to a non-trivial solution of ax equals 0. So then we have the following. The columns of a matrix A are linearly independent if and only if the equation ax equals 0 has only the trivial solution. So let's look at some special cases. Sometimes we can determine linear independence of a set with minimal effort. In the first case, if we have a set of one vector, we're going to consider the set containing one non-zero vector, v1. So this is a vector that does not have all zeros in it. Then the only solution to my equation x1 v1 equal to the 0 vector is the trivial solution when v1 is not the 0 vector. So if I have to multiply my vector v1 by some constant and end up with zeros, the only way to do that is if x1 was equal to 0. That's the only way that that would happen, because we were told to begin with that v1 was not 0. So since the only solution is the trivial one, then we know that v1 is linearly independent as long as it is non-zero. So that's the key. When our set has one non-zero vector, then we know that it's linearly independent without doing any work. Our next special case is a set of two vectors. So let's look at an example. We're going to let u1 and u2 be these given vectors, and v1 and v2 be these given vectors. So in part A, we want to determine if u1 and u2, the set containing those vectors, is a linearly dependent set or a linearly independent set. So notice that our vector u2 is a multiple of u1. It's actually 2 times u1. Therefore, we could solve this equation here by simply subtracting u2 over to the other side, and we would then have 2u1 minus 1 times u2 is equal to 0. And so we've set up a linear dependence relation simply by solving the equation we had, noticing that we had multiples. So this means that the set of my vectors u1 and u2 is a linearly dependent set, since we could come up with a linear dependence relation. Now let's look at the set containing our two vectors v1 and v2. And we want to determine if it's linearly dependent or linearly independent. So just by looking, you can probably tell that v1 and v2 are not multiples of each other. So we're going to go through a semi-proof here. And we want to suppose that I do have a linear dependent relation with constants c and d being multiplied by v1 and v2 and added together, and that that's equal to 0. So in that case, we could then solve our equation for v1 and get that v1 would be equal to negative d over c times our vector v2, assuming c was not 0. But this is impossible since our vector v1 is not a multiple of our vector v2, which means then that c must be equal to 0. Similarly, we could have taken our original equation here and solved for our vector v2 instead and gotten that it was equal to negative c over d times our vector v1 if d is not 0. But this is impossible since our vector v2 is not a multiple of v1, and so then d must be equal to 0. So then what we've just shown is that for this linear dependence relation to exist between v1 and v2, c had to be 0 and d had to be 0, which means we have only the trivial solution. Since we have only the trivial solution, this means that the set of vectors, there's the set containing my two vectors v1 and v2, is a linearly independent set. So let's look at what we just discovered. Two vectors v1 and v2 are linearly dependent if and only if one is a multiple of the other. Otherwise, they're linearly independent. So we see here the example v1 was equal to 3v2 in this case right here, and we were able to then solve it and get a linear dependence relation. From our example we just looked at, here are the vectors u1, u2, v1, and v2. And we're going to look at the graph. First, if I graph u1, it's at 2, 1, which is right here. So this is u1. And if I graph u2, it's the vector 4, 2, which is up here. And we see then that it simply lies in the straight line with u1. So this is linearly dependent. And they'll lie in a straight line. Now we look at v1 and v2, and v1 was at 2, 1. And then v2 was at 2, 3, which is up here. And so we see that these are not in a straight line. They are not multiples of each other, and so they are linearly independent. My third special case is a set containing the zero vector. So it may contain other vectors, but it has also the zero vector in it. To talk about this one, we're going to look at Theorem 9. If a set contains the zero vector, then the set is linearly dependent. So based on this theorem, if you have a set of vectors and the zero vector is in there, then you know it's linearly dependent. So let's just look at an example to prove this. If v1 equals 0, then my set of vectors v1, v2, and v3 is linearly dependent, since I can write a linear dependence relation by simply writing 1 times v1 plus 0 times the other. So I have a non-trivial solution, and I know that I'll get 0 since v1 was equal to the 0 vector. So anytime I have the 0 vector, it's linearly dependent. And now my fourth special case is a set containing too many vectors. So let's look at some terminology. Any set of vectors v1 through vp in Rn space with n entries is linearly dependent if p is greater than n. That is, there are more vectors than there are entries in each vector. For example, the augmented matrix might look like this. And so we see our column of zeros here, and we know we have 4 columns, so that means we had 4 vectors, and we had 3 rows, or 3 entries in each one. So I have more columns than I have rows. Since p is greater than n, then there must be a free variable. And if I have a free variable, then I know I have a non-trivial solution. And so the columns of A then are linearly dependent. In this example, I want you to answer the question of whether these sets of vectors are linearly independent or not, and give a reason for each answer with the least amount of work as possible. So look back at the special cases we just looked at, and we'll talk about your answers in class. Lastly, we want to introduce Theorem 7. An index set S containing the set of vectors v1 through vp of 2 or more vectors is linearly dependent if and only if at least one of the vectors in S is a linear combination of the others. In fact, if S is linearly dependent and v1 is not 0, then some vector vj, where j is greater than or equal to 2, is a linear combination of the preceding vectors. So here's an example of what we're talking about here. I have this linear dependence relation, v1 plus 2v2 minus 5v3 plus 2v4 equals 0. I could then solve that for v4 and write it as v4 equals negative 1/2 v1 minus v2 plus 5/2 v3. So then I see that my vector v4 is a linear combination of the preceding vectors. So not all the vectors have to be, and you notice it says if at least one of the vectors is a linear combination of the others. And so notice here that it says if S is linearly dependent, then some vector is a linear combination of the preceding vectors. So in this case it was our last vector. So it doesn't have to be every vector follows this, but we have at least one, and that is Theorem 7.